That should be the acceleration of it as it goes down the ramp. It doesn't matter what the mass is. Yeah, Coy.
And J formula wouldn't it be sine because cosine is horizontal?
Because this angle here is theta, and this wedge right here, the opposite side is the one that's going down the ramp.
I'm just so used to cosine being horizontal and sine.
Yeah, and that's one of the reasons this throws some people off. A different way of doing the exact same thing. Now, whenever I draw my angles, they almost all look like they're in between 40 and 50 degrees. It's hard to tell. If I actually tried to draw a 20-degree angle there, well, 20 is on the smaller side, and apparently didn't like what I was doing there. All right, so I've got a small angle, and I'm breaking my weight up. Weight is acting down, and I'm breaking that up into part that's down the ramp and part that's perpendicular to the ramp. I need to create a right triangle here. If I draw my angle much smaller, more realistic, I can see from this drawing right here that whether it's W sine theta or W cosine theta, the smaller of the ones is the one that's down the ramp and the larger one is into the ramp. So I could also just calculate them both and go, oh, the smaller one, that's down the ramp. Other questions up to here? All right, given our angle, what is our prediction for the acceleration of the cart as it goes down the ramp? .367. And again, what are the odds? All right, so first off, I want to make sure that the bottom of the track doesn't move, because then we're redoing the angle. We're going to use the motion sensor again. And I'm thinking it's not recharging here. Nope, it is charging. We're at 5%. All right, so I'm gonna put the cart on here. Now anything that is too close to it, anything within about 15, 16 centimeters will not be registered, but since we're doing the method that we are, we don't have to be as precise. We just need to make sure we take a piece of the curve that is more acceptable. One other issue, I really don't want the cart banging into this straight on like that, so I'm going to put this box here just so that it crashes into that. And actually, before we get the acceleration, we have this W sine theta down the ramp. What is W sine theta? It's calculated. .745
Yeah.
units.
Newtons.
Without the question mark. All right. So we should be able to actually see how close we get on that.
Let's see, just go into.
So I'm going to zero the force sensor. So if that is the part of the weight that is acting down the ramp, that should be the amount of force that keeps it from going down the ramp. So I can put this right here, make sure it's in the grooves, and then put this right there. And we are getting, now my hand's shaking just a little bit, but you can see it's 1.7 something. And we had 1.745, this is looks like slightly higher than that, but still, we're within 100th of a Newton of what we predicted, or at 100th placeable. All right, so now, all right, the angle didn't change until it hit. I thought this one would be easier. All right, so I don't care about, the bottom one is the force, there's nothing on the force sensor, so that's just statistical fluctuations right there. So show graph one. This is the part I care about in here. We'll zoom in. I want to take a part where it was part of my parabola right there. Do curve fit, analyze, curve fit, position. I want quadratic. And my coefficient of my quadratic term is 1.6637. So my position, 1.6637 t squared plus some other stuff I don't care about. What is the acceleration?
3.3274.
And our prediction, 3.367. Pretty darn close, especially if you've done enough physics demonstrations and you realize how many of them just are crap. Yeah. Ooh. You were thinking it, if not saying it out loud. Questions to hear? All right, why don't we take, I'll pause the recording. We'll take a small little break, stretch legs, get a drink of water, come back. We'll do some throwing stuff, or mentally. And fun will be had by at least one person.